I designed and built a 3D printed, solar-powered, remote-controlled catamaran. But before I show off the build process and discuss some of the engineering considerations that were involved, I want to explain my reason for starting this project in the first place. A few months ago, I found myself inspired after watching a video on a channel called rctestflight, where this guy named Daniel shows off his solar-powered catamaran with autonomous capability. In the video, he uses the catamaran to tow himself in an inflatable kayak around a body of water following a 20-mile autonomous waypoint mission. My first thought was that I would love to do something similar, only at the time I didn't know anything about RC electronics or solar-powered systems. So I decided right then and there I was going to start this project and use it as a literal and metaphorical vessel to teach myself about solar power generation and RC electronics. I then did what any self-respecting millennial engineer would do. I went online and watched dozens upon dozens of YouTube videos to learn the basics and figure out which parts I would need. I then drew up this basic schematic to illustrate how all of the major electronic components would wire together to form the RC system for my catamaran. I started getting really excited about this project, and then I went on Amazon and eBay and got intimidated by the fact that there are thousands upon thousands of each one of these components, and that I would need to figure out exactly how to choose the right ones such that they work together and didn't blow each other up. I eventually realized that I would need to cross-reference the information on these technical data sheets to confirm that certain components would work together without issues, and that the best way to do that was to do something that I absolutely love. That is, build an Excel spreadsheet. I then started manually inputting critical specifications for these components into the spreadsheet, knowing that I could write equations to check the value of those specifications to see whether or not they were suitable for the application. After a few days of work, I ended up with a spreadsheet that effectively acted as a logic ladder. I was able to arbitrarily pick RC components and have the spreadsheet tell me whether or not they were compatible. I selected all the parts I wanted, then ordered them either through Amazon or AliExpress. Eventually all the parts arrived and it was time to wire up the RC electronics to give the system a test run. With the RC system working, it was time to move on and model the catamaran using Fusion 360. This weird looking boat is a 62 centimeter long remote controlled catamaran whose battery life is extended using a 25 watt monocrystalline solar panel that's shown in green. Hiding the solar panel gives us a better look at the structure. Here you can see that each of the symmetrical hulls are joined together by a common deck section as well as two aluminum rods that pass through the bow and stern to provide extra stiffness. Taking a closer look at the hulls reveals that they are actually split into three sections. This was done so that I could 3D print each of the hull sections on my desktop FDM 3D printer and then reassemble them after the fact to form a complete structure. The lids, as well as the deck section that joins both of the hulls, were designed with the same intent. Viewing the catamaran from the front reveals that each of the hulls has a relatively rectangular shape. Mono hulls tend to have a V-shaped hull in order to improve their roll stability. However, catamarans don't need to worry about this because roll stability for them is entirely determined by the spacing of each of the hulls. That means that the frontal shape can be redesigned in order to maximize buoyancy as a means of minimizing their wetted area, thereby reducing drag. Looking at the catamaran from the stern reveals that each of the hulls has its own prop and rudder. Of course, catamarans can be steered entirely using differential thrust. However, if one of the motors were to die, the vessel would lose control authority and would only be able to drive around in circles. By adding a rudder to each of the hulls, even in the event of one of the motors burning out, the vessel would still maintain its control authority and be able to navigate back home. Of course, this is done at the expense of increased cost and system complexity. Hiding the lids reveals the inside of the vessel. Here you can see that the lids will seal onto both the hulls and the deck with the help of these purple gaskets, which will be cut from a sheet of closed cell foam. You can also see the solar charge controller, shown in blue, which will live inside of the deck compartment. Taking a section along the length of the port side hull offers a better view for the remaining components. Zooming in, we see that we have the battery, the electronic speed controller, the servo motor, the rudder, the prop and prop shaft, and finally, the water-cooled brushless DC motor, which takes water from a port at the bottom of the hull and then ejects it through a port at the stern. Now it's time to touch on some of the engineering considerations, which are super important for the design of the catamaran, but incredibly boring for a YouTube video. So I'm just going to fly through them. I input mass and density parameters for all the components in this Fusion 360 model so I could accurately estimate the catamaran's mass and the position of its center of gravity. Knowing this mass, which is just below 7 kilograms, in combination with Fusion 360's volume measurement tools, I was able to determine the height of the waterline in static equilibrium conditions. It ends up being just below the deck, which is perfect because it means the catamaran won't be submerged when fully loaded. You could import this 3D model into a computational fluid dynamics program to run an analysis that determines the location of the centers of pressure and buoyancy. Knowing those in combination with the positions of the centers of thrust and gravity, you could do a static and dynamic pitch and roll stability characterization for the catamaran. The next step was to 3D print all of the hull sections, the deck, and the lids. I used Fusion 360 to export all of the 3D printed parts as STL files, which I then sliced in Prusa Slicer using the Prusa ASA filament settings. I chose white ASA filament for this project because it's UV resistant, it has a higher toughness than either PLA or PETG, the white color was so that it absorbs less radiation when sitting in the sun, and finally, ASA has a special property where it can be dissolved in acetone. This means I could use acetone to fuse together the sections of the hull, meaning that I wouldn't need to use either adhesives or epoxy to join them together. I could also use the ASA to smooth out any layer lines, eliminate imperfections, and help waterproof the hull, which is a common problem for 3D printed boats. The downside to using ASA filament is that it is notoriously difficult to 3D print. It tends to warp and has poor bed adhesion. The strategy to overcome these downsides is twofold. First, you can build an enclosure around your 3D printer. The enclosure has the effect of keeping the ambient temperature around the part being 3D printed relatively uniform. It also helps prevent drafts, which can cause issues with layer adhesion and bed adhesion. The next thing to do is using an ASA slurry to improve bed adhesion and prevent warping. This is done by mixing an 8:1 ratio of acetone to ASA and letting the solids dissolve to make a sort of ASA juice. You then paint this juice onto your bed and let it dry fully before starting your print. Just keep in mind that using this technique can cause build plate adhesion that's too good, meaning you can potentially damage your build plate when removing the part, like I'm about to do. Woo! It was finally time to assemble all the components. In my opinion, this is the scariest but best part of any project. You never really know if everything's going to fit together the way you hoped, but if it does, it's so damn satisfying. I started by using a soldering iron to melt brass M5 threaded inserts into the connection points that would join the 3D printed hull, lid, and deck sections. I then bolted together the sections using a whole bunch of M5 by 8mm shoulder bolts, which are common throughout the project. At this point I realized that the 3D printed parts had warped a little bit, so I ended up having to force them into position to ensure correct alignment. I also realized that the mating surfaces between the hull sections didn't sit perfectly flush, leaving small gaps that would definitely not be waterproof. Fortunately, I was able to seal these gaps by applying a slightly thicker version of the ASA juice that I made previously, only this time using a 4:1 ratio of acetone to ASA. Once it dries, this goop effectively welds the sections of plastic together, making a watertight seal. Just to be safe, after filling in the cracks, I applied a moderate coat of a slightly thinned version of the juice to the exterior surfaces of both hulls. I also filled up a spray bottle with pure acetone and then went absolutely crazy spraying every inch of the inside surfaces of both hulls just to ensure that it would be waterproof. Rinse and repeat this process for the deck and the lids and you end up with a waterproof vessel. After the surfaces dried, they ended up with a brushed texture that I didn't like, so I ended up sanding all the wetted surfaces with fine grit sandpaper and then reapplying a slight mist of pure acetone just to smooth everything out. I then melted the remaining threaded inserts into the top surfaces of the deck and the hulls, making sure to cut off any excess overflow material to ensure a flat surface for the lids to mount to. The next step was to measure out and cut two 15-inch lengths of 3/4 inch aluminum tubing. These aluminum tubes have three purposes. First, they help align the hulls such that they are parallel and square when you are fusing the deck to both hulls. They also increase the strength and stiffness of the structure. Without them, it would be way too easy to accidentally break off one of the hulls. And finally, they act as convenient mounting points for the 3D printed brackets that can accommodate multiple sizes of solar panels. After inserting the aluminum tubes and adding the deck, I noticed that there was still a small gap between the deck and both of the hulls. These gaps were definitely caused by warping of the 3D printed hulls. However, it was easy enough to fix. All I had to do was apply more of that acetone ASA slurry to the gaps, clamp it shut, and allow it to dry, thereby creating a waterproof seal. I also made sure to use slurry to fill the gaps where the wire pass-throughs join the deck and the hulls. The next job was to install the propeller shafts. I started by filling the shaft tubes with a synthetic grease that was suitable for marine applications. I then applied a generous amount of grease to the housing that holds the shaft tube, as well as to the shaft itself, just to make sure everything would remain waterproof. The last thing I'd want to do is have to remove the shaft tube from the hull after discovering a leak. So I just made sure to apply a generous amount of grease to every surface I could think of. Next came the motors. I applied a thin layer of grease to the internal O-rings of the motor coolers and then slid the motor coolers onto the motors themselves. The idea behind the motor coolers is that while the boat is moving, enough dynamic pressure is built up on the underside of the vessel to force water through the vinyl tubes into the motor cooler in order to extract heat that's generated from the motor and then reject that heat out the back of the vessel. With the motor coolers on the motors, I fastened the motors to the motor brackets using 5 M3 by 12 mm shoulder bolts. In hindsight, it would have been smart to put some thread locker on those bolts, but whatever, live and learn. I then installed the shaft coupler that connects the 4 mm drive shaft to the output shaft on the motor. It was a bit of a challenge to maneuver my hand inside of the hulls holding an Allen key in order to tighten the grub screws that are part of the shaft coupler, but I got the job done. I then lowered the whole motor assembly into the hull, connected the motor's output shaft to the shaft coupler, and then fastened the motor bracket to the hull using 2 M5 by 8 mm shoulder bolts. And just to be safe, I applied a generous bead of waterproof silicone caulking to seal the joint between the shaft tube and the hull. The next items to install were the rudder assemblies. Just like before, I started by filling the shaft sleeves with synthetic grease. I applied a liberal amount of grease to every surface I could think of, including the shaft and the housing that holds the shaft sleeve, and then shoved everything into place. This next step was kind of tricky, but was necessary in order to measure out and cut the correct length of push rods that connect the servo horn and the control arm for the rudder. I installed both the control arm for the rudder and the servo and screwed both into position. I then went out and bought these cheap marking flags from Home Depot because they use a 1.75 mm diameter steel wire that's perfect to act as the connecting rods between the control arm on the rudder and the servo horn. They're easy enough to cut using a set of pliers and then bent into that Z shape that's useful for installing into the holes of the servo horn. I fit 2 of these rods into the holes of the control arm and then reinstalled the control arm back onto the rudder. This allowed me to hold the wires in position above the servo horn in order to mark the position of the bend. I then removed the control arm and the connecting rods and then used my pliers to make a Z bend at the positions that I had marked. At that point, it was easy enough to insert the connecting rods into the holes of both the control arm and the servo horn and then reinstall both of those components back into the hulls. Once again, there wasn't a whole lot of clearance in this part of the hull, so it was challenging to tighten everything down, but with a little finessing, I managed to do it without stripping any of the screws. And just like I did for the propeller shaft tube, I applied a generous bead of waterproof silicone sealant to the joint between the rudder shaft tube and the hull to help prevent leaks. It was then time to install the ESCs. This was easy because they're just held in place using strips of Velcro tape and then plugged into the motor using those 3 wires. It doesn't really matter how you connect the wires because you can always switch any 2 of the 3 of them to reverse the direction of the motor. Next, I installed 2 lengths of 1/4 inch ID clear vinyl tubing that circulate water into the motor cooler. The water supply tube gets fed into the hole at the bottom of the hull and then plugged into the inlet port in the motor cooler. The exhaust tube gets plugged into the outlet port of the motor cooler, routed through the hull, and then fed through the hole at the stern. And just like before, I applied more waterproof silicone sealant to prevent leaks and then cut off any excess material that was protruding past the hull to make everything flush. Up next, I installed the 6 amp hour 3-cell lithium polymer batteries from a company called HRB. Just like for the ESCs, the batteries attached to the battery tray using strips of Velcro tape. The battery tray then gets fastened to the hull using 4 M5 by 8mm shoulder bolts. And just to be safe, the battery is also held in place using an extra strip of Velcro that wraps around the battery tray. There was probably enough extra space to be able to add 2 batteries per hull, but doing so would have increased the weight, raised the waterline, and moved the center of gravity forward, which I didn't want to do, so I didn't try it. It was then time to make the gaskets for the lids. I started off by printing 1-to-1 images of the gaskets on separate pieces of paper. I then used the flashlight on my phone as a backlight to align the features of these gaskets before taping the sheets of paper together. I used the paper templates when cutting the gaskets from a roll of 8-inch thick neoprene closed-cell foam. It was important to use closed-cell foam so the gaskets would remain waterproof and compress evenly when the lids are bolted on. At this point, everything was wired up and ready to go, so I started putting the lids on, and then I immediately discovered a design oversight, which was that when the lids are fastened down, there would be no way to access the power switches for the ESCs, which means you'd have to actually turn the ESCs on and then spend 5 minutes bolting the lids back on. To fix this, I decided to remove the switches from the ESCs and embed them in the lids for the hulls. I cut off the switch, and then I repurposed a servo extension wire which I spliced in line with the switch to act as a sort of quick connect so that whenever I removed the lid, I could easily disconnect the switch and not have to pull out the ESC as well. I'm really bad at soldering, and I have a cheap soldering iron, so it was a bit of a hassle, but totally worth it for the practice, as well as for the convenience of being able to remove the lids for the hulls without having to also remove the ESCs. It was easy to install the switches in the lids. I just marked their position with a pencil and then heated up an X-Acto knife with my heat gun so I could effortlessly cut through the plastic like a hot knife through butter. I then shoved the switches in place and then sealed the gaps using more of that acetone ASA slurry. I also made sure to go back and update the CAD files to include a hole for these switches, just so that if I ever wanted to make new lids, I wouldn't have to cut holes again. I think they turned out pretty good. These are the brackets for the solar panel. They just slide over each end of the aluminum tubes and then fasten into place. You then add another M5 bolt which feeds into the threaded insert at the top, and then that goes through a corresponding hole that's been drilled into the aluminum frame of the solar panel to pin it in place. I decided it was worth it to apply a bit of grease to both sides of the gaskets just to help the lids seal better. It's probably overkill, but better safe than sorry, and getting a bit of grease on my fingers was a small price to pay to ensure that the lids would be waterproof. Up next, I installed the radio receiver into the deck using a bit of Velcro tape, followed by the MPPT solar charge controller, also using strips of Velcro tape. This one is made by Genasun, it's a 10 amp version, and is compatible with lithium polymer batteries. It was then time to install the solar panel. I chose a 25 watt monocrystalline solar panel made by a company called NewPower because this panel in particular has the lowest mass per watt of any monocrystalline panel that I could find that would fit on my Catamaran. I also like that it has a blocking diode in the junction box, it has a waterproof rating according to IP65, and it has a sturdy double wall aluminum frame that's easy to mount to. The next challenge was to install the solar panel in such a way that I could remove it without having to unscrew the terminals in the charge controller. I decided to splice a Dean's connector between the solar panel and the charge controller so that I could easily unplug the panel whenever I wanted to do maintenance. Of course, this meant more fumbling around with wires and pretending I know how to solder. At one point, there was too much heat from the soldering iron, and it caused the heat shrink tubing to shrink before I could slide it over the connection. I also completely ran out of solder at one point and kind of just left the joints half finished, and me being me, I didn't bother to check the continuity before wrapping everything up in electrical tape, so fingers crossed that everything is connected properly and it doesn't catch on fire. I also ended up poking a hole through the front of the deck with my soldering iron to make a convenient pass-through for the wires that connect the charge controller to the solar panel. And now that I just made a big hole at the front of the vessel, I had to go back and fill it up and seal it using more of that waterproof silicone. I also went back and updated the 3D model to include this hole, so if you 3D print these parts later, don't worry, I got you. At last, it was time to connect the batteries in parallel and fasten down the lids. This is a tedious process because there's 24 individual M5 by 8mm bolts that need to get fastened. I probably could have come up with a better, or at least faster way of sealing the lids. However, I like this method because it ensures that the gaskets get compressed evenly, making it more likely for the lids to be waterproof. And because there's about 450 Canadian dollars worth of electronics inside of this vessel, I'm glad to know that it's sealed properly, even if it took longer to do so. With the solar panel in place, this boat was finally finished. It took about 4 months to design and build, as well as maybe 600 Canadian dollars for all the parts and materials, which I know is a lot, but considering this is my first time using RC electronics, I'm really happy with how it turned out. Man, I was so stoked for this project to be finished. I couldn't wait to take it to a nearby lake and put it through its paces. And then I remembered that it's currently February in Toronto and that it's minus 15 degrees Celsius outside and snowing, and that I would probably need to wait until at least April for the lakes to thaw before I would be able to test it out. Fast forward 2 months, Lake Ontario is thawed and I'm ready to take the boat out for its maiden voyage. I gave it a quick test on dry land just to make sure everything still worked after being in storage, and then resealed the lids and got it ready to launch. There we go. Okay. All right. Okay, that's literally as low as it goes. I can turn it. Thank you.
Woo!
Woo!
This is the first time out?
First time out.
There you go, you did well, buddy.
It sits pretty low in the water, eh?
Lower than you wanted?
It's about where I thought it would be, but it is pretty low. At this point, I realized the catamaran was a bit too heavy. I also noticed that it had a tendency to pitch upwards whenever I would increase the thrust past a certain point, which is why you see me driving it really slowly. So I decided to bring it back to dock and remove the solar panel to eliminate a bit of the weight. I don't feel any water in it. Good. Should be a lot later now.
Yes, it's a lot higher up.
There we go. Oh my god, it sings faster too.
Woo!
Oh, it turns on a dime though.
So fast. Oh shit!
Oh, I got a little image there. So now I know it's impossible to put this.
Yep.
Good work! Overall, I'm super happy with how this project turned out. Of course, there's always room for improvement. If I could change one thing, it would be to incorporate a way of adjusting the angle of the propeller shaft so that you could adjust the pitch of the boat no matter how fast it was moving, similar to the way the trim feature on an outboard motor works. But that's a project for another day. I had an absolute blast making this boat, and I learned a ton in the process. I hope you enjoyed this video. Thank you for watching. I'll see you next time.